Let's wait until Joe gets back. That way he's not kind of out. And then other than that, okay, you guys should have gotten your spirals. That way, if your graphing quiz corrections were in there, let's take a second. Let's get it ready to turn in while we're waiting on Joe. Huh? Get your quiz corrections out, your graphing calculator quiz. Does anybody need a staple real quick? You could have done it on the paper that's corrected for calculation asked if you could put it on a separate piece of paper. Have it ready, we'll turn it in as soon as we get in. You'll have it like underneath your composition. Got it? Alright. Here we go. Reciprocal functions. We talked yesterday how reciprocal functions have a domain problem because, by definition, a reciprocal function has a denominator. What's true about all denominators? With domain. What's not allowed to occur in a denominator?
Negative on 0.
Oh, negatives are allowed. Remember, negatives just aren't allowed where?
0.
No, negatives are actually allowed in the exponent too. We just have to think about it differently. Yeah. Negatives aren't allowed in the square root. Zeros aren't allowed in a denominator, right? So, let's see. What we didn't get to talk about yesterday? What are these dotted lines called again? Good. And so the one that's up and down, straight up and down, would be a vertical asymptote, right? Graphing calculator, quiz correction, rich and all. And then the other one would be? Okay, I need to expand your horizons just a little bit. When you first learned a horizontal asymptote, when you first learned a vertical asymptote, probably your teacher said something like it's a line that the function will get closer and closer and closer to, but never touch, right? Okay. If you look up, well, be careful. Some nerds are kind of dirty, but if you look up math means online, there is one with like Gandalf by a vertical asymptote. It's like thou shalt not pass. Vertical ones you cannot go through. You cannot. The function cannot pass through because the domain does not exist there. The domain doesn't work. There's an error. Vertical asymptotes, you cannot cross through. Why am I saying that? Why am I making such a big deal about it? Because horizontal asymptotes, you can. Dun, dun, dun. See, told you it'd be exciting. So, horizontal asymptotes. They are like vertical asymptotes. And somehow a function does need to be getting closer and closer and closer to, but never touching to the left. Closer and closer and closer to, but never touching to the right. But here's the tricky part. In the middle, every now and then, maybe it crosses through. The point is not what goes on here. Okay? Quite that first shadow. The point isn't what goes on in the middle. Calm down. The point is what's going on to the left and to the right. So I just want to let you guys know because a lot of kids, they just kind of, I don't know, they start to freak out whenever I ask for a horizontal asymptote and you have some funky graph that crosses through. They're like, no, it does not exist. There is no horizontal asymptote. But there is. Look right here. It's getting closer and closer and closer and closer to, but never touching to negative infinity. And it's getting closer and closer and closer, but never touching to positive infinity. Horizontal asymptotes, it only matters what's going on to the left, to the right. We'll talk more about that in a future section. But there you go. Oh, this one doesn't have a vertical asymptote. Oh, okay. Good. You're right. There is no vertical asymptote. This graph, there's only a horizontal. Now, looking at this one, I just wanted to bring that up because we're introducing the idea of horizontal and vertical asymptote. And I'm saying vertical asymptote, no function can ever pass through a vertical. Just think, right? End up with his vertical asymptote. Nope, never, thou shalt not pass. But I just wanted to let you know, even though this function does not cross the horizontal asymptote either, I'm not saying that no function ever can. Does that make sense? Just because I'm showing you this one that doesn't mean that no function ever can. Yes, Jonathan Reeves likes Switchfoot, and so he's quoting their song lyrics. In case you're wondering what's going on. He went to the concert recently. It's pretty exciting. Okay, so let's move on from reciprocal. We have two more ones to talk about. Actually, two specific ones and one general category. General category first. Piecewise. General category first. Piecewise functions. While you guys are just writing down, there's barely anything to write down. Just pass it your quizzes. Let me go ahead and grab them from you. Put everyone's back in the room. Go see what looks like if you need to. Alright. Pass them straight up. Straight up towards you. Anyone? You decided to turn them in early? I'll come back to the ones that are still coming up. Are you missing? Okay. I think you guys already turned. Let me back. Piecewise functions. Well, they're called functions. I guess there could be piecewise relations, which means I could do something like f of x equals function notation. But what's different about a piecewise? Remember what comes next? Piecewise functions, a function defined in pieces, multiple pieces. So is it just one function? Well, actually the answer is yes, but is it one function with only one piece, one line, one... I'll just say one piece. With one piece? No, pieces. No. Which means I need to get ready for multiple. Now how many pieces could it have? As many as it wants. 2, 3, 10, 12, I don't know. Now, we don't want to go too crazy, so let's just say it's one of the crazy ones that has 3. So it might have one function is comprised of, we're just making an example with 3 different pieces. So you could have 3 different equations in here with 3 different pieces with 3 very different behaviors. You could have a linear piece, you could have a quadratic piece, you could have a reciprocal piece, you could have a square root piece. As we get farther, you could have an exponential or a logarithmic piece or a trigonometric piece. Here's the struggle. So, if there's nothing defining what the pieces can or cannot be, can I say necessarily how this function is going to behave? Now, let me just give you some examples of inequalities. This could be x less than, we'll just put some number a, x less than 1, x less than -5, x less than 10. This could be x does not equal a. Oops, no. That doesn't make any sense. It does, but not in this context. Sorry, x equals a. And x greater than a. This is one way that pieces could be. It's all about one x value, a. And one piece is what's going on to the left of a, one piece is what's going on to the right of a, and one piece is what's going on at a. That's one way of doing it. Another way that you guys have probably seen is I could do something like x less than a. You don't have to change yours, that's okay. We could also have that's right. X greater than or equal to a and like less than b. Then x greater than or equal to b. There are different ways the inequalities can even appear. You could have an inequality where you have like a sandwiched x value where it's you have one piece going to the left of a, one piece going on in between a and b, and one piece going on to the right of b. Anyway, there are different ways the inequalities can appear. There are different ways the functions can occur. There are even different numbers of pieces. So here's the struggle. I can't really tell you much about a piecewise. What I can tell you is the quick note I want you to write down. And the quick note is the pieces of a piecewise, meaning the different functions that are comprising the entire function. The pieces do not always connect. Now there's a snappy math term for when the pieces do connect, we would call them continuous. When they don't connect, we call them discontinuous. You guys have heard things like removable, non-removable discontinuities last year. We're going to be reviewing holes and vertical asymptotes and all that jazz. But I just want you guys to realize that when we have piecewise functions, even though it's like, hey, G is going on for a while, and then, oh, G stops, and then H is going on for a while, and H keeps on going, and then H stops. Sometimes the pieces do connect. This could be my G, this could be my H, and this could be my J. Sometimes they might connect. Sometimes they might just happen to meet up at that point where one of them is going all the way up to but not including, and the other one fills in and keeps going. Sometimes they do connect, but more often than not, they don't. So, all of that to say, sometimes we have to be careful or watch out for what I call the separators. So one more quick little description. Just it's my way of teaching doesn't necessarily mean every math teacher everywhere is going to call these. But I like to call A and B separators. Once again, this is not like a vocab term in your book. But A and B are separators. They separate the domain. They split up the domain. And then I call these the pieces of my piecewise function. Separately defined functions. And then, of course, we've already talked about these as the domains. You could use these, or you could state these as the domains of each of the pieces. You could also think about them as the inequalities or the x intervals. If you guys remember, isn't domain x intervals anyway? Values of x's, where something works or doesn't work. Just a few different labels. I'm not even going to put this in a yellow box because technically this is not a parent function. This is just a chance that we had to kind of talk about a piecewise function or how piecewise functions move, behave, and how I kind of define some of the different notations of a piecewise. Now, the reason that we introduced piecewise functions is because these two, the last two parent functions we're going to talk about, are piecewise functions. These two are piecewise functions. We have the absolute value function, and we have the step function. Now, this is a little messy. I already wrote down absolute value, so let's not write it twice. Let's get rid of him. There we go. If any of you guys were working on homework last night, some of you that picked up your homework spirals, you would have seen the funny step function and not quite known what to do with him because, can you guys see the step function, otherwise known as the greatest integer function? There are two names for it. Depends on where you're dealing with it as to how the author describes it. It could be called the greatest integer function. It's also known as the step function. One way of showing it is how they do in your book, which is with two brackets. Two brackets, no parentheses, two brackets around an x or around something. It could be around an x plus 1. It could be around a 2x minus 3. But when they put the two brackets, they're talking about this function. And the other one you're more familiar with, we even did it at the beginning of the year, and it's known as absolute value, just the straight bars, right? Now yesterday, you guys did an awesome job because I asked you what some of the different transformations were, and we came up with the shifts, the shrinks, the stretches, the reflections, the flips. And someone also said the absolute value. Nicely done. Absolute value can be put around any function, and there are certain transformations that it does. So when I talk about the parent function of absolute value, I'm just talking about the most basic, just around x. But we will talk about eventually, as we get deeper in transformations, what absolute value does to any function, but we're just going to start with the parent function if it's only around x. But first, the step function. Okay. The step function is a piecewise, and here's why. Here's why. It's actually an infinite one, so I'm not going to write down all of its pieces, because if you think about it, how long is it going to keep stepping for? What do you guys think? Yeah. How about as you go to the left? How long is it going to be stepping for? Stepping down for? Okay. And each step, I'm telling you, each step is a different piece. So are we going to write down infinitely many pieces right now? No. But what I am going to do is show you at least a few of them, okay? So here's the weird thing. I'm going to have a dot, dot, dot. I'm going to do a couple pieces, and I'm going to have a dot, dot, dot. Because there are infinitely many pieces. Let's start for x within. I'm actually going to use interval notation, so it's just going to be a little bit quicker. Where am I going to start? I'm going to start right here. Start this piece, and I'm just going to go this many pieces. That should be enough. So I'm just zooming in on this part of the graph right now in this piecewise function down below. Okay. So if x is in between, let's start with this first step. Kiddos, what x's are included in this first step? Can you tell with the closed and the open? -2 to -1. Good. But including -2 and excluding -1. Do you see what I'm doing? Including -2 and excluding -1. Why? Where's the filled in or where's the solid dot? Exactly. So it's including -2, excluding -1. Question, what's the y value here? Can you tell with the tick marks? Exactly. This function equals -2, -2, -2, -2 for everything in between -2 and -1. What are values in between -2 and -1? -1.1, -1.75, -1.9, right? All of those. -2. Now, what's the next piece? What's this step? What's the domain of this one? -1. And isn't it going to be the same thing, bracket and then parentheses? -1 to 0. What's the y value now? -1. Good. You guys see how the y value is just going stepping up each time? So what's the y value going to be in the next piece? And then? Okay, so we're only doing a few of these. 0 and then 1. You guys find the pattern? What's the domain of when the function is 0? What? 2. Just follow the x's, remember? Left to right, x's. So 0 to 1, not 1 because it's open. You guys see how it's always just a length of 1? Always open on the right. Let me give one more. Just following the pattern, -2, -1, -1, 0, 0, 1. Don't even look at the graph. What's the next one? 1 and 2, and keep it open. Okay. Greatest integer function. It's kind of hard to see this one when we're in the negative numbers. It's a little bit easier in the positive numbers. Kiddos, what are some numbers in between 1 and 2? 1.5, sure, what else? 1.3, 1.2, 1. No, right? 1.00001. What does the greatest integer function, the step function, do? Greatest, highest, integer. What's an integer? A positive or a negative whole number, right? So no decimals, no fractions. Wait, no decimals, no fractions. Look at all the y values. No decimals, no fractions. The x values have decimals and fractions. So if we put in something like 1.7, we put in 1.7 to the double brackets, what does the function do? 1.7, it's going to round down. So what the step function does, what the greatest integer function does, is it says, even if it's 1.7, we still just treat it as 1. Even if it's 1.9, doesn't matter, it hasn't reached 2 yet, we still just say the greatest whole number in 1.9 is 1. The greatest whole number in 1.99 is 1. The greatest whole number in 1.23 is 1. What's the greatest whole number if you were to plug in x is 3.7? 3. What's the greatest whole number in 52.1? Does that make sense? You're always rounding down, in a sense. Round negatives get tricky. Based on what I just said, what if I was to plug in -2.3? What would you think right away? A lot of you would think -2. You're like, it's -2 and a little bit more. Here's the problem. If I was to show you up here, -2.3, does that fit in between -2 and -1? No, it's not -2, but think about a number line. Remember how I said 1.7 is 1, right? 2.7, 2.3, 2.2, all of those are 2. Think about it down here. What was the one I gave you? -2.7? We're always rounding down. We're always rounding down. If I have -2.3 or -2.7 or -2 point anything, if you round down, where do you go? -3. It's weird to think about, and yet it's true. The reason why most of your brains go to -2 is you're like, oh, hey, 2 is a lower number than 2.3, but the problem is you're in the negatives now. And when you're in the negatives, the lower number, the more negative number, is actually -3. Just trying to let you guys know, because if anybody did get this far in homework, the negatives got tricky. And if you didn't get this far in homework, when you get there, the negatives get tricky. So, let me do a quick example off to the side. If I was to ask you for, or to simplify, double brackets, 1.7, double brackets, 50.9, double brackets, negative 1.2. We've basically done all of these. I just changed the numbers just a little bit. What would you guys tell me on 1.7? 1. Think the number line, 1.7 is right here. You round down, it's 1. 50.9, if I was to go all the way out, 50, a little bit higher, 0.9, what do I round down to? Let's see if you can still do it. Negative 1.2, I go negative 1, a little bit lower. What do I round down to? Negative 2. Negative 2. Does that make sense? Yeah. It's tricky. Now, can anybody think of a practical application of the step function? I guess you could do that actually, Nick, because you could say, I want the stairs to be a certain distance, right? And if you're trying to make like a platform mold or something to pour the concrete, you could say, okay, well, if I want the stairs to be what, like a foot wide? That's not too bad. Like a foot wide. And you could say, okay, from the base of the building, if I need stairs to come away or maybe up to a level area. Long story short, if you're trying to measure out distances and measure off, it's like for this entire distance, whether I'm a foot and an inch or a foot and 6 inches or a foot and 8 inches, all of that needs to be at the set same height for the mold to make that stair, right? So whether I'm an inch past a foot or 2 inches past a foot or 3 inches past a foot, I need to be on the next stair. And once I hit the second foot, okay, now it's time to make the third stair and the fourth and the fifth. Okay, I guess that kind of works. I was thinking like away from construction, away from like something that looks like steps. So that's how it gets hard. Is there anything in life that even if you plug in decimals, what only matters is the whole number? Anybody ever parked in the parking garage where you had to pay money? Yeah. Question. Do they charge on the seconds, the minutes that you're in there, or usually the hours and the half hours? Hour. Yeah. So if you're in there 31 minutes, and it was every half hour, well, it's like downtown, right? Every half hour, you pay like a higher charge or an extra $2 or whatever. Okay, so if you're in there 31 minutes, what's the machine going to tell you? Oh, it's okay, let's round down to 30? No, it doesn't round down. What is that piecewise function going to do? It's going to round up. It's going to be the same idea as a step function. They don't care if you were in there 31 minutes, 37 minutes, or 59 minutes. They're still going to charge you the same, you're in there an extra half hour, right? Does that make sense? But then, is that a step function that would go on forever? But most of them have like a daily max, and then if you're in there more than a day, they're like, we're killing you. That's that. Then it's a whole other charge. But anyway, long story short, there are times in life where even if you're 1 minute over, 5 minutes over, 10 minutes over, the charge is still the same. Usually might be swapped up, but not rounded up. You could think of other applications. That's the easiest one that I can think of right off the top of my head is a parking garage. Parking meters? That one? No, not so much. Those ones you can go more like by minutes. It's not by seconds, so in a way the seconds don't matter. The minutes do, but there again. Anyway, let's go ahead and just say that I forgot. We have one more function. Did we even talk about absolute value? Nope. Absolute value. Hopefully you guys have the graph of him. Poor little absolute value chilling over there. Why is he broken? Maybe you don't realize he's broken. What was he before the absolute value came in? Just a line. Y equals x. Take out the absolute value of y equals x. We talked about him yesterday. He's just one of these guys, right? So the line is supposed to keep going down forever. So what happened? It got broken because what can't be negative if you put absolute values around the outside? Oh, the x can be negative. I can plug in -5. But what do I always get out? Okay, so the y's are always positive. Does that make sense? Yeah. You can put in positive or negative x's. You can even put in 0. But what do you get out? Only positives. So the portion that used to be there before with negative y's, what happened to that? Disappeared. So when you put an absolute value around the outside, any negative y's flip up. And we'll talk about that when we talk about transformation. But for right now, I'm actually not talking about the transformation of absolute value. Instead, I want to talk about the function absolute value and why I call him a piecewise. I want to talk about the function absolute value and why I call him a piecewise. Because he behaves two different ways based on the x's you put in. Same thing over here. We needed separate pieces because depending on the x you put in, the value is going to change. An absolute value, depending on the x's you put in, something different happens. And you guys know this. Because if the x's are greater than, or I could even say equal to 0. What kind of numbers are greater than or equal to 0? Positive. If you plug in a positive, you can tell me in words. Plug in a positive, what do you get out? Okay, let's change that a little bit. You put in a positive and you get the same thing out, right? So you put in 3, you get out 3. You put in 5, you get out 5. You put in 1.2, you get out 1.2. You put in 0, you get out 0. For all the numbers greater than or equal to 0 that you put in, it comes out the same as what you put in. So any numbers greater than or equal to 0, what you put in comes right back out. Well, what happens? Well, first of all, what inequality am I going to put for the second piece? All the negative numbers. X less than 0. I did inequalities because I didn't have room to do intervals. In case you were wondering. That was as extensive as my reason went. Positives and zeros, plug in, comes out the same. Negatives, here's where it gets tricky. I could show it to you and you would all get mad at me. So I'm not going to show it to you yet, I'm going to explain it to you. You plug in a negative, what comes out? Okay, now so mathematically, what can we do to a value? What can we do to an x that would make it have the opposite sign? But how many of you would have gotten mad if I said absolute value sometimes means a positive x and absolute value sometimes means a negative x? Why would you get mad at that? Because you're like, no, absolute value is always. But this makes it a positive because what x's go in the x spot? So these are negative numbers. If I take a negative of a negative, what's going to happen? Yeah. So absolute value. If you don't like absolute value, and if graphing absolute value is hard, he's really just y equals x half the time, and he's y equals negative x the other half the time. All right, kiddos. I'm going to go ahead and draw real quickly yellow boxes around each of these. These are technically also parent functions. You're going to see them in homework. And I think those of you that did homework, aren't you allowed to use your graphing calculator every now and then in this one? Yeah. Okay. And the reason is we haven't talked about transformations yet, so they're not expecting you to be able to do everything by hand yet. Why does the word yet scare you just a little bit? Yep, homework's due tomorrow. Homework number 6, not 5. Don't know why it says 5. But remember, our goal today was not just finish 1-6, it was to start 1-7. So here we go. Let's start. And let's start talking about those transformations that we just introduced very yesterday. Real quick, in section 1.6, does it expect you to be able to do all the transformations by hand yet? No. So in that homework, use the calculator when they say to use the calculator. It's okay, it's an introduction. Hopefully you remember lines behave a certain way, parabolas behave a certain way. It has you deal with domains and ranges. Some of the stuff we did in notes. But remember, 1-6, you don't have to do everything by hand. Those of you guys updating your table of contents, awesome idea. You'll be far less stressed on the data test than others. If you guys writing, I'll do some writing. Stay focused even though I'm not looking at you. I do it over by the TV. Referring to what I just wrote on the board to help us kind of stay oriented. Orientation. Oh, Mr. Michaels in chat yesterday. Were you disoriented? Did you find orientation? Yeah, that was crazy. I did not. Well, as Mr. Strike said, a lot of us didn't know about what she experienced. Unlike you guys, I remember what happened. It's very different from someone who's in the midst. But orientation. Sorry, trying to stay on focus. On task. To try to help you stay oriented in the midst of all these different transformations. There are basically two things, only two categories that you have to be able to distinguish or remember or memorize. One category is which transformation. You see adding, subtracting, hopefully as you're writing right now, adding, subtracting, that's a shift. Which transformation? For right now, adding, subtracting, that's a shift. That's one connection. Which transformation? But then, the second piece is what direction? And specifically by direction, I would say horizontal, vertical. Because horizontal has positive, negative, right, left. Vertical has positive, negative, up, down. They both have positive negatives, but the point is, are you moving horizontally or changing horizontally, or are you changing vertically? If you're trying to move right and you're supposed to be moving up, well, your orientation is off. So, first of all, what type of transformation? Second of all, in which direction? Do you guys see what I mean? As you look at, I'm going to get my highlighter out because there's a lot of words up here, and I realize that you don't necessarily need to memorize all these words. But first of all, we did just talk about how we have pluses and minuses. Whenever you're adding and subtracting, yes, that is going to be a shift in mathematical snazzy way of saying that. That is going to be a translation. Snazzy math term, translation. The easy way of remembering it, shift. Long story short, the shape doesn't change. You're not stretching, you're not compressing. All you're doing is just moving what's already there to a different location. So adding and subtracting, first of all, I'm going to show you that right here. You're just adding and subtracting. It's going to be a shift. Now I'm going to go ahead and take away all of those highlights because that gets a little confusing. On the board, what do I say next to horizontal, guys? On the inside. Question. 1, 2, 3, and 4. Which ones are on the inside in the map? Okay. And 3 and 4 are both what kinds of change? Horizontal. Now we do have to remember, of course, horizontal when you're on the inside. When a change is happening to the argument or the input, like we talked about with function notation. Yes, we have to get oriented and be like, oh, weird. Minus subtracting is to the right? Oh, that's different than what I would think. adding is to the left, well, that's different than what I would think. So that's something that you've seen before. I just want to make sure that you guys are able to see the adding, subtracting, to know it's a shift, and then to see it on the inside and know it's horizontal. Now, what do I have next to vertical up there? On the outside to the parent function. Do you guys know, in this notation, you can see vertical on both of these. Who's representative of the parent function in these equations? F. H is the changed function. It takes the parent function, or the beginning, and it adds or subtracts C on the outside. So when you have a plus or a minus, once again, it's a shift. On the outside, it's going to be vertical. And what do you guys notice about the addition? Where does it head? The exact same way you would think, right? If you're adding to the lines, you go up. If you're subtracting from the lines, you go down. So we also maybe can think of something else. In that vertical seems to be what we're used to. Just an easy way of studying it. You can say vertical makes sense. If you add on the outside, well, vertically it's going up. If you subtract on the outside, well, vertically it's going down. Horizontal. That's very different than you might first think. Now, if you know what everything means and you have it memorized, well, that's going to be exactly what you're thinking. But it's different than you think in the sense of the subtraction actually moves positively, the addition actually moves negatively. Now, that's translations, shifts, adding and subtracting, inside, outside. Outside vertical, inside horizontal. So if I was to give you something like, let's see, what's one of those parent functions from yesterday? Go to the transform function. If I was to give you the directions of sketch by hand, not using a graphing calculator, the following, and let's do a couple of them. If I was to do h of x equals x squared plus 4, and then g, I just skipped 10. G of x equals x minus 5 squared. I'll make them blue. I'll make them green just so that they're color-coded. Question, what's the parent function before we even do any of the transformations whatsoever? X squared. X squared. Somebody squared x squared plus 4. X squared is the parent function. Do you remember the representative points from yesterday? How do we get x squared on the graph? Precisely, not just like a little like something close. Yeah, that's not too bad. So what are some points on x squared? 0, 0, right? Plug in 0 to x squared, and then do my little parent function up here. I have 0, 0. What else do I have? 1, 1. Okay, that should be enough, right? For the one side? That's enough. We can have a little arrow and have it keep going, but that's good enough. And we can do negative 1, 1. Remember, copies on the other side. And negative 2, 4. Okay. What am I going to do with this little guy when I go to graph H? For what? Because you take the y's, or the f of x squared, and what do you do to the y's? Make them all higher. So instead of 0, 0, where are you going to be? 0, 4. Instead of 1, 1, where are you going to be? 1, 5. Just add 4 to the y's. Instead of negative 1, 1, where are you going to be? Negative 1, 5. Instead of 2, well, maybe you guys can do it. I think I got it from here. Right? It's going to eventually branch out also. What am I going to do with G? It's on the inside. It's horizontal. It's backwards what I think. So even though it's a minus, I'm headed to the right. So instead of 0, 0, where am I going to be? Instead of 1, 1, where am I going to be? 6, 1. Instead of negative 1, 1, I'm going to be at 4, 1. Do you guys see how if I have the points, maybe I can do the transformations a little quicker and then just swoop, there it is, right? So when you are trying to do transform functions, start with the parent function, look back in section 1.6, get a few points down, and then do what you need to. Either add to the y's, add to the x's, or in other examples, subtract from the y's, subtract from the x's, and maybe we'll be able to do these transformations a little easier than we've done in the past. Pause. Before we can do this, though, what do you need to practice in 1.6? Yeah, you need to practice with all those parent functions. So kiddos, finish up 1.6 homework. Maybe you can start 1.7. If you can't, go for it. I'll see you guys tomorrow. 1.6, do 1.7. See if you can start. Bye. Everybody got their homework files, right?
I saw a bunch of people out there though. Yeah, because I went to the bathroom, they're all in front of me. I was like, nope.
How we go?
You okay?
Yeah, I'm okay.
A little bit of chipmunk?
Yeah, still in pain. But this side is still
Yeah.
So I'll be here after school tomorrow.
Okay, sounds
I
good.
can't do it today because I have another thing today.
No, I understand that.
Yeah.
You have to stagger us, I get it. I get it.